Welcome to Curious Orbit. Today, we're going on a journey far, far beyond our own solar system. We're heading past our galaxy and diving deep into the very origins of everything we know. We are going to explore the oldest light we can possibly observe in the entire universe. It's a story full of cosmic mystery, ancient echoes, and the fundamental building blocks of reality. Just imagine, for a second, receiving a message from a time before Earth even existed. I mean, way before the sun was born and long before the Milky Way looked anything like it does today. We're talking about a literal signal that has been traveling through the endless void of space for more than 13 billion years. And no, this isn't science fiction. Scientists can actually detect this ancient lingering signal right now. In fact, it's washing over Earth every single second. Part 1. The universe's ancient afterglow. So this ancient afterglow is called the cosmic microwave background, or, just the CMB for short. And this spectacularly old light is, without a doubt, the single most important piece of evidence we have for piecing together our cosmic history. It holds all these incredible secrets about how our vast universe began, how it evolved, and really why it looks the way it does today. But that naturally brings up a pretty massive question. How could this light possibly survive for over 13 billion years, crossing the entire cosmos just to reach our detectors today? Well, to understand how this ancient signal made it, we've got to flash all the way back to the very beginning, to a time when the universe was just this entirely different, incredibly hostile place. Part 2. Clearing the cosmic fog. Okay, let's dive into this. So the early universe actually started out in this extremely hot, dense state. Imagine an incredibly thick, opaque, glowing cosmic fog where light literally couldn't travel freely. Why? Well, because you had these extremely hot charged particles constantly slamming into photons of light. The photons were basically just trapped, being scattered over and over again. But as space continuously expanded, it began to cool down. Then, at step 3, which happened roughly 380,000 years after the Big Bang, something absolutely monumental changed. The universe finally cooled just enough for electrons to grab onto atomic nuclei. Suddenly, neutral atoms formed. This epic event is known as recombination. Because there were far fewer free-roaming, charged electrons bouncing around to scatter those photons, we finally reached step 4. Light could travel freely. The universe literally became transparent. And get this, some of those exact photons released in that very moment have been traveling completely uninterrupted ever since. You'll often hear scientists describe the cosmic microwave background as a baby picture of the universe. But we need to be very precise here. It's actually not a photograph of the exact instant of the Big Bang. Instead, it's a snapshot from that moment of recombination, roughly 380,000 years later. But to put that timeline into perspective, imagine compressing the universe's entire 13.8 billion year history into just one single human lifetime. On that scale, the CMB would show us the universe when it was only a few hours old. That is how incredibly early we are looking. It's just mind-blowing. Part 3. Stretching the ancient light. So the really crucial point here is that this light was released back when the universe was incredibly hot and glowing brightly. But if you try to look for it today, you're not going to see blinding white light. So what exactly happened to all that blinding light over billions of years? Well, the answer lies in something called cosmological redshift. Remember, the universe has been constantly expanding ever since the Big Bang. And as space itself expanded, the wavelength of that original, ancient traveling light was literally stretched right along with it. The original radiation has been stretched out so much over 13 billion years that today, its wavelength has shifted all the way down into the microwave part of the spectrum. And that is exactly why we call it the cosmic microwave background. And because it's been stretched so dramatically, it's also cooled down immensely. Today, we detect this microwave radiation as an almost perfect thermal spectrum, and it corresponds to an unbelievably cold temperature of about 2.725 Kelvin. Just to be clear, that is barely a couple of degrees above absolute zero. The blazing, unimaginable heat of the early universe has cooled down into this faint, freezing whisper. Now, knowing that this signal is incredibly faint, entirely invisible to the naked eye, and practically freezing cold, you might be wondering, how in the world did humanity ever manage to discover this ancient signal in the first place? Let's pivot for a second to the human element of this incredible story. Part 4. Mapping the cosmic COBEs. The actual discovery of the CMB is a truly fascinating story. Back in the 1960s, these two radio astronomers were working with a very sensitive microwave antenna, right? And they kept detecting this persistent background noise coming from literally every single direction they pointed their instrument. They furiously tried to eliminate every possible source of interference, but the signal remained stubbornly present. It turned out it wasn't their equipment at all. It was the sky itself. Eventually, the scientific community recognized this radiation for exactly what it was, the predicted afterglow of the hot early universe. And that initial discovery? That was really just the beginning. By 1989, NASA's COBE mission measured the spectrum of the CMB with extraordinary precision, confirming its incredibly cold thermal temperature. Then came the satellites that actually mapped the entire sky. The WMAP mission in 2001 measured tiny fluctuations across the cosmos in fantastic detail. And later, in 2009, the European Space Agency's Planck mission produced an extremely precise, full-sky map of these fluctuations. This allowed scientists to study the statistical patterns of the early universe in just remarkable detail. Now, mapping those tiny fluctuations is absolutely critical because the CMB isn't actually perfectly uniform. There are these incredibly tiny variations in both temperature and density. Over billions of years, gravity went to work and amplified those tiny differences. Slightly denser regions pulled in more gas. Dark matter structures began to grow around them, stars formed, galaxies assembled, and eventually, massive galaxy clusters developed. So those microscopic temperature variations you see in the CMB map, they are literally the cosmic seeds of all the massive structures we see spread across the universe today. By studying the exact statistical patterns of these cosmic seeds, scientists can actually investigate the universe's overall geometry, how it expands, and really its entire history, which inevitably leads us to one of the biggest questions of all. What is the universe actually made of? Part 5, Decoding the Invisible Universe. Measurements of the cosmic microwave background provide incredibly powerful constraints on our universe's total energy budget. When scientists decode the complex patterns hidden in this ancient light, it reveals a broad picture that is remarkably consistent yet fundamentally mysterious. Now, what's really interesting about this slide is just how little of the universe we can actually see. Look at this breakdown. Ordinary matter, the stuff that makes up stars, planets, gas, and, us, makes up only a tiny, tiny fraction of the total cosmic energy budget. A much larger fraction is dark matter, which we cannot directly observe. And completely dominating the entire present-day universe, that's dark energy. The universe is mostly invisible to us, and the CMB is what helped scientists build and rigorously test this profound picture of our cosmos. But while the CMB answered some enormous questions about our universe's composition, it also created another major mystery. Think about this. If you look at the universe in completely opposite directions, billions of light years apart, the CMB temperature is extremely similar. Why on earth is the CMB so unbelievably uniform across such vast, distant stretches of space? Part 6, Horizons and Lingering Mysteries. This exact puzzle brings us to what's known as the horizon problem. Basically, how could distant regions of the early universe, regions that are billions of light years apart, have such incredibly similar conditions? If we just go by the simple, standard expansion of the universe, those vastly separated regions would never, ever have had enough time to exchange information or equalize their temperatures. To understand this lingering mystery, we really have to draw a strict line between hard evidence and theory. On one side, we have our observational evidence, the highly uniform CMB temperature maps that we directly, physically measure. On the other side, we have the theoretical explanation proposed to solve this horizon problem, which is called cosmic inflation. Inflation proposes that the universe underwent an extremely rapid exponential expansion very early in its history, which stretched tiny quantum fluctuations to massive uniform scales. But it is absolutely crucial to remain objective here and distinguish between the hard, observable facts the CMB directly shows us and the theoretical models, like inflation, that are proposed to explain it. In fact, scientists are still actively investigating the exact physics behind inflation today. So, all of this incredible, universe-defining data comes from a snapshot taken roughly 380,000 years after the Big Bang. But it really begs the ultimate question, doesn't it? Can we look even further back? Can we actually see what happened before the cosmic fog cleared? Well, think of the CMB as a sort of cosmic fossil. It perfectly preserves information about the early universe at a very specific stage in its evolution, but it also acts as an absolute observational boundary. Because the early universe was that thick, opaque plasma fog we talked about, photons just couldn't travel freely. Therefore, the CMB is effectively a hard, impenetrable wall for the earliest electromagnetic light we can ever directly observe.
To investigate epochs earlier than the CMB, we literally cannot use light. Instead, scientists have to rely on other avenues of evidence, things like theoretical physics, particle physics, and potentially gravitational waves.
The photons reaching our detectors today have been traveling through an expanding universe for billions of years, beginning their long, lonely journey long before the Earth or the Milky Way even existed. They still surround us, quietly carrying the earliest chapters of cosmic history. If you could decode one mystery hidden in the cosmic microwave background, what would you want to know? Tell us in the comments and subscribe to Curious Orbit for more space science.